Hello, everyone. Welcome back. Welcome to our new lecture series on organic chemistry. So the next topic and the last topic we're going to be covering of new material in the course. So in this topic, we're going to be covering, let's see, we're gonna talk about all of the different kind of compounds of carbon, some of the nomenclature. We'll look at um, functional groups and how they're going to change the molecular properties, what kind of reactions they can be involved in. We'll discuss polymerization and a couple of methods for how polymers form. We'll also look at, in the end, we'll look at biomolecules and proteins, so natural polymers and macromolecules, although it remains to be seen whether or not that'll be tested, so it's likely to be as a separate kind of segment tacked on to the back end of this. Okay, so getting started. Organic chemistry, what is it and why do we call it organic chemistry? So really, organic chemistry is going to be the study of carbon compounds. So that's meant to be a C. Let's see if we can finish it off. C, carbon. Okay. So it can also have, say, hydrogen, oxygen, nitrogen, sulfur, the halides. All of these combined with carbon in a molecule are quite normal. Why do we call it organic chemistry? Well, again, this is one of those historic things that back in the day they were thinking that any molecule that came out of a living organism was somehow special, somehow had this vital property that made it different than non-living matter. Eventually, that was disproven, famously, though a little bit apocryphally, by a total synthesis of urea. But there were also ways to make, say, acetic acid quite early on. That was originally thought to be a strictly biological molecule. Both of these are examples of organic molecules, and the name just sort of stuck. So we normally now consider organic chemistry to be things that are mostly carbon-based, and then inorganic chemistry will be the rest of the periodic table, really. And for living things, we tend to group that now into biochemistry. So biochemistry would be the study of chemical processes inside of living organisms. So specifically things, say cellular processes of respiration or chemical synthesis, but that happen inside of living things. Just to be clear, there really is no difference between the chemistry that goes on inside of living things and the chemistry that goes inside of non-living things. Living things just happen to be a chemical reaction that's self-sustaining, self-replicating, self-regenerating in ways that is quite complex compared to the stuff that we tend to do in the lab. We're really not competing yet. So carbon, what does make carbon so special? Why is it that we have thousands upon thousands of useful and different compounds that really have a carbon backbone? Well, it has everything to do with its position on the periodic table. So carbon with its 4 electrons in the outer orbit, so that's right in between having a full octet in either direction. So you can imagine that it's either going to donate or accept its 4 electrons across either single, double, triple bonds, depending on the hybridization of the carbon. So it's really flexible in what it's going to bond with. It's a very, we want to anthropomorphize it a bit, it's a very social atom. So happy to get along with all kinds of things. Again, not surprisingly, its intermediate electronegativity allows it to combine with something that's quite electronegative. So oxygen, the halogens, even fluorine, so things like Teflon, where it's bonded to fluorine, but also to electropositive elements. So there are organometallics, where we've got carbon bonding with a whole range of metals, really, and obviously especially hydrogen. So what about other elements that can compare? Something like silicon. We always kind of imagine alien life being silicon based. Like why don't we see that? And in fact, we don't see it. So anywhere in nature, there's no silicon based a molecule that's an analog for any carbon molecules. So something that would be doing the job of a carbon in say a DNA type molecule or a protein type molecule. It's just not found in nature. Silicon, so being it's directly underneath carbon, but another row down in the periodic table, and by virtue of that, changes its chemical properties. So silicon binds a little bit too weakly with hydrogen and a little bit too strongly with oxygen. So even in water, the hydrogen can be displaced off of silicon. But as soon as silicon starts to bond with oxygen, it continues to bond with oxygen until it forms a very strong mineral. And that's why most of the silicon in the earth is just as sand. It's just silicon oxide. Okay. So frankly, no, it can't do the job. Carbon is a special place on the periodic table, and that reflects in the molecules that it forms around us. Okay, so to start to classify the literally tens or hundreds of thousands of molecules that can be formed with just carbon and a few other atoms, we start to break them down by type. A lot of the names are, again, just historic. They're not super descriptive, but you know, that is the memorization part of organic chemistry. I'll say right up front, a lot of people get afraid of organic chemistry. I think it's fine. I liked it. It's a second-year course, and if you stick around long enough to play with it, you can actually have a lot of fun in organic chemistry. It's very creative, where we get into the synthesis of molecules. It's a fun lab to be a part of. There is the memorization in the points of thinking about the functional groups and the different names of the different nomenclature that's behind it. But if you can get past that and just start to think about all of the molecules it makes as machines or as parts that have a 3D shape, that require that 3D shape in order to do the job that they're there to do. If you have a little bit more of a mechanical background or a mechanical mind, then organic chemistry is going to be something that you're quite good at. But just to kick us off, let's talk about alkanes. So these are the simplest organic compounds that we have. Hydrocarbons. So hydrocarbons specifically are anything that has only hydrogen, and carbon. Okay, that shouldn't surprise you with a name like hydrocarbon, that it just has hydrogen and carbon. That doesn't really limit it for how many possibilities we can have for this molecule. Most commonly, we talk about straight chain alkanes. So this is just a single chain of carbon-carbon bonds bonded together just by, we would have single bonds, also known as saturated molecules. And we call them saturated because everywhere where we have a carbon, 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 and we're working our way along the chain, each one of these carbons is absolutely full of hydrogens. There's no possible bonding site that we don't have a hydrogen on it. If we didn't, it would be double bonded to another carbon, and that's going to be a different type of molecule, different type of name. But alkanes are exclusively sp3 hybridized with 4 bonds, 2 of them to carbons and 2 of them to hydrogens. So the general formula we've got here for an alkane is going to be a certain number, n carbons, and then we'll have 2n plus 2 hydrogens. Where does that 2n plus 2 come from? We'll have a look over here at what we were doing with the carbon chain. If we want to end this off, and we're not going to connect to another hydrogen or another carbon, we'll connect to another hydrogen. So there's 1, 2, 1, 2 hydrogens on each of these carbons along the body of the chain. And then at the end, we have 1, 2 hydrogens, and then plus a third hydrogen to cap it off. And the same thing's going to happen at the other end. So each of the carbons has two hydrogens attached to it, and then plus we have an extra 2 to just cap off the chain. Okay, so that's our 2n plus 2 hydrogens for n carbons. Okay, so that's our ending in methyl groups with methylene groups in the middle. Okay. Full formula, if we wanted to write it out completely, we'd do something like methyl group, okay, CH3 plus CH2, CH2, as many as we needed to do, CH2, that's perfectly enough, and then CH3, cap it off again. We could also abbreviate that more or less by saying CH3 and then CH2 in brackets with how many there are. So in this case, we have 1, 2, 3. So put a little 3 in the corner. And then CH3 again to cap the other side. How else we can do it, of course, is just write down we have 1, 2, 3, 4, 5 carbons there. So 5 carbons and then 2n plus 2 hydrogens. So 12 hydrogens. And this is going to be a pentane. And that actually is where we're going to go on to the next page. So when we're naming these take the suffix ane, so it's an alkane. All of them are going to be called -ane at the end. And the first part is going to, for the most part, follow Greek roots, although the first couple are special. I don't know why. So for just a single carbon, the methane, the problems that we're having was as a greenhouse gas with the methane and the regulations out in Alberta. This is the molecule we're talking about. So a very small, very light, single carbon, 4 hydrogens. Difficult to push around, easy to burn off, but not exactly environmentally friendly. Okay, following with the second one, ethane. So same suffix, and now it's just ethane on the front end. With 3, propane, just like you'd put in a barbecue. It's a gas at room temperature. It's a liquid in your propane tank, only because it's under high pressure. Followed by butane. Same stuff. If you ever had a Zippo lighter, or maybe one of your older relatives had a Zippo lighter, butane torch would be what's in it. Pentane doesn't really get used that way because we start to move into liquids at room temperature. Hexane is a liquid at room temperature and is used as an extractant solvent sometimes when we're trying to get out more oily components, biofuels. Like if you ever got out of like oils from a rapeseed to use at a biofuel, like hexane might be the solvent we use to extract it. Heptane. Now you can really see that we're moving into the Greek roots. So pent, hect, hep. Next one, of course, is octane. The standard form for gasoline. What we're looking for is the concentration of octane, right? So high octane fuel or low octane fuel. 9 carbons, we get a nonane, and a 10 decane. And we can go on like that. So we can have a undecane, a dodecane, a trisdecane, and it just carries on through all of the, again, the Greek roots there. Okay, for drawing these guys, you've got a few options. For methane, fewer options. So usually it's just going to be a carbon, 4 hydrogens, quite straightforward. Either drawn as 4 bonds, just straight horizontally and vertically. We can also just write it down, CH4. And if we want to think about it in 3 dimensions, if you'll remember back to September, the sp3 hybridized carbon Each of the bonds are actually at 109.5 degrees apart. So these aren't really in a single plane to each other. Two of them will be, of course, but then the other two, one's going to come forward out of the page, and we'll draw that with a filled in wedge. And the one will come kind of going into the page, and that's done as a series of dashed lines. Okay, and so if we want to show the 3D, if we want to show the 3D geometry of the molecule, that's how we can express that, of course, just writing it down on a 2D piece of paper. Ethane, we can do the same, more or less the same things. So now we'll connect all of the hydrogens to the two carbons that are bonded together. C2H, now we have 6, right? Again, 2n plus 2. And we can do the same thing here. So carbon, carbon, these will be, of course, just on a plane in line with the page. We can have one hydrogen in each that's going to be on the same plane as well. And then for each of them, one will be coming out of the page, one going back into the page, and the same for the other carbon. H and H. Okay, and so for this, you can kind of imagine these two, like this would be near and far away from you, kind of sitting like a bipod, and this would just be like a monopod, I guess, sitting on the back end. Octane, you're really not going to make me draw 8 carbons out, because it'll look very much the same. But as we get towards molecules, or especially just single chain carbons, it gets a little bit much drawing in all the hydrogens. We know they're there. If it's not shown that there's a double bond between the carbons, we always assume that all the points are going to be saturated with hydrogens anyways. And we know that the carbons are just going to be wherever there's a change in direction of the line. So what we can do instead is just start with a single carbon and go 1, 2, 3, 4, 5, 6, 7, 8. And just that line is enough to symbolize for us octane, okay? Because we know that at each of the ends of the lines, or where there's a change in direction, that's going to be a carbon. So we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. There's no double bonds between them. We can assume that all of the positions are going to be full of hydrogens. So this is going to look a lot like octane to us, okay? Good. So we already see that these are sigma bonds, so it's just a single bond connecting each of these hydrogens. If you need a little bit of a reminder about the sigma bonds versus pi bonds, either go back and check your notes or just, I guess, Google it. But remembering that a sigma bond is just a bond that goes directly between the two nuclei, right? So when I was teaching this in my class, I mentioned it would be like, since there's only a single bond, it's like nailing a board to another board with just a single nail. This allows it to rotate around each other. You'd need a second nail in order to stop that rotation. Same thing with bonding. With the second bond, the molecule is not free to rotate around that bond anymore. But where we just have one, then there's really nothing stopping it. So let's have another closer look, say at this ethane. And I want you to imagine if you were, well, I guess a lot smaller for one thing, and looking down the barrel of these two carbons in the carbon-carbon bond. Okay, so what you would see is, here's the two hydrogens that are acting as our bipod and the one that was on top. So since we're looking down the barrel, again, between the two carbons, we're not going to draw in a right C for the carbon because we know that that's there. And so this is going to be our near one. And for the far one, we'll draw it as a circle. and have the bonds coming out of it as just lines attached to that circle and back, okay? So those will represent its hydrogens coming out the backside. So this one in the middle would be the monopod over here. And the ones kind of up in the air are our ones up in the air here, okay? So that's another way of drawing this bond and a way of thinking about how those are going to rotate around. So if they're all quite equally spread like that, it's going to have the lowest energy. And we're going to call that a staggered conformation. But because it does allow for rotation, it is possible that we would have, there's no sense rotating both sides. We'll just keep the front one steady. And on the back one, we could have the other hydrogens stacked in line with the ones in the front. So this would look like if we had our two hydrogens now all on the same, lined up with each other, okay? And this would be the eclipsed conformation for obvious reasons. Again, it's because they're going to be blocking one another. If you looked at this, if you were comparing the energies of these ones as we rotated, say around, well, I guess let's call this theta. So we're just going to rotate one of them around the other. You would see, let's start them in the eclipse position, I guess. So that's going to be at a higher energy. And as it gets staggered, it's going to go lower and then work its way back up to a higher energy as they get stacked again, back into eclipsed. And then it'll work lower again as they get staggered and back up and back low again. And then it's just going to continue on that as we roll around theta. So this will be the staggered conformation. So we can write in here, it's the staggered conformation. Will be more stable at lower temperatures. And you can imagine if the groups, so groups thinking if we replaced hydrogen with any other atom. So let's say chlorine, for example. So something that's quite a lot larger and bulkier, if that had to roll past itself, so that would be, let's say we'll stagger them. We'll have them first staggered so that the chlorines are quite far apart from each other. So that'll be the lowest. And then, okay, a chlorine is going to be eclipsed with a hydrogen, so that's a little bit more. And then now the chlorines are getting closer to each other, so they're not going to be quite as low, and we don't get as low energy. And as the chlorines come and become eclipsed with each other, we get the highest energy. Back down again. Now it's just a chlorine and a hydrogen, and the chlorines return to their furthest staggered position, and we get back to the lowest energy possible. So that's going to, again, really more strongly favor the staggered conformation as the groups on those on this ethane get larger. Okay, properties of alkanes. So thinking about all of the examples that we walked through as we were naming them. So non-polar, less dense than water. So if we're thinking about oils, or gasoline, then you already know that that's going to float on water. Immiscible with water, yeah, so it's going to create a layer of the lighter alkanes on top of water, so we produce an organic layer. Some of the skills that you will get in the lab next year will be how to separate those and extract just the water layer, the aqueous layer, or just the organic layer, depending on what it is you're trying to produce. Considered chemically unreactive, you might think that, say, octane is quite reactive. I mean, that's where we're getting our gas, or propane, you know, we're cooking our burger. But honestly, that carbon-carbon bond or carbon-hydrogen bond is relatively strong. And a lot of chemistry goes into trying to find ways to activate or open up these bonds to be able to do chemistry on them. So a lot of inorganic chemistry actually is focused on opening up these bonds just to allow other chemistry to happen, to change the molecular shape. Intermolecular forces, so thinking about what's going to cause various alkanes to bond with each other versus other things. Move away from hydrogen bonding, so there's no oxygens here, there's no nitrogen, there's no fluorine or any really strong polar force to cause hydrogen bonding, even though there's a lot of hydrogen. So we're looking more at van der Waals, dipole, to a certain extent. Even sometimes if these are in water, just the fact that water would rather be together, that it's going to force these molecules together just to minimize their surface contact or minimize their surface area in the water. So it's not so much that these are attracted to each other, it's that water is attracted to itself and it just wants to force these things away from it. So smaller chains, gas at room temperature. So yeah, propane, methane, butane, we've already talked about those. Intermediate chains, getting to liquid at room temperature and pressure. So these would be the hexanes and the heptanes, octane again. Longer chains, so thinking quite long a chain, are waxes and plastics. So kind of at the extreme end of this, we can look at like polyethylene, which is a polymer, but it's really just a very, 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 very long chain of saturated carbon bonds. So that's where I'm going to leave this section for this video, and we still have more to say about alkanes with branch chains and with naming alkanes, but I think we'll leave it there for now. We'll pick up those ideas on the next video. So thanks for watching, and talk to you then.